My name is David Cameron. I'm a developer advocate at Stream Native, and welcome to my talk, Building Scalable and Resilient Event-Driven Applications with Apache Pulsar. Again, as I mentioned before, my name is David Cameron. I'm a developer advocate. I'm a committer on the Apache Pulsar project. I'm also the author of Pulsar in Action. I was former principal software engineer at Splunk, where we ran Pulsar at scale as a large messaging system. And as you can see from the logos below, I've worked at quite a few different companies, from Amazon A to Zappos Z and everywhere in between. I also have a lot of experience working with distributed systems and event-driven architectures. So let's start by defining what an event-driven architecture is. So event-driven architectures are designed to have an asynchronous communication between event producers. These are things that happen in the real world, true business events, something like somebody logs onto your web page, or a truck moves down a route, or something in your inventory management system gets scanned into the system, something appears at the warehouse and gets scanned in. That generates an event. Something happened that says this business event happened, A happened, and I publish that information asynchronously to an intermediate message broker that holds this information, and then event consumers that are interested in these events can consume those automatically, asynchronously themselves, and react to them accordingly. So again, if something comes into the warehouse and 5 different people need to react to it for different reasons, they all have their ability to consume that asynchronously and process it, and that allows processes to scale much more efficiently. They can react to larger data volumes. There's nothing done, there's no sequentially, there's no dependencies between the two, so it's much more scalable architecture. And some of your event producers here shown on the left, as I mentioned before: sensors, IoT devices, web clicks, smart devices, anything you want, sensor readings, etc. Event consumers are things like microservices, web applications, and as I'm going to mention today, Pulsar functions are one of those things that's a very good use case for implementing event-driven architectures. So those of you, since it's a Pulsar conference, I'll skip all the preliminary stuff and tell you about why Pulsar is a great case for being a message broker for an event-driven architecture. It is scalable, horizontally scalable, very fast, supports the messaging semantics that are required for an event-driven architecture vis-a-vis queuing, work queues, topics and subscriptions. So it is an ideal candidate for that. It serves as a great place to store the data that gets published asynchronously from the event producers, and the consumers can consume from it. But in addition to that, not only do you get the message broker capabilities, but you have built on top of Pulsar as a serverless lightweight compute framework called Pulsar Functions. For those of you not familiar with Pulsar Functions, it's a Lambda-style architecture that allows you to, run individual pieces of code in response to an event. So it has a, very, very fluid EDI or event-driven architecture style in general. But to start with, I want to mention that it has its own computing infrastructure, right? And so it supports different runtime options, including processes. So you can have what's called function workers and dedicated resources that will run these Pulsar function instances. But they also support, in the primary use cases, for Kubernetes. You'll find out why that's important later, because as we're mentioning before, we're talking about resilient and scalable event-driven architectures, right? Your applications want to be able to dynamically respond to an increase in data volume and not be overwhelmed by this data volume and crash, and then your system's down. And Kubernetes is sort of the key to that. Pulsar functions also allow you to write your individual code logic that respond to an event coming in to a system, right? So again, this is an event-driven architecture design. Having something that is designed with a fluent EDA style API makes it a perfect fit, and Pulsar functions are a good fit for that. And then you can scale these together, right? They're stackable. They're kind of like Lego blocks. You can have one Pulsar function feed into another one, feed into a third one. And it makes it very easy to reason about building these things. An event comes in, what do I have to do to it? I can massage it, put it out to this topic, the next function can do its thing, and so on and so forth. It allows you to very quickly build these processing logics without having to stand up a whole other complex system like Flink or Spark, or have to learn a complex API to do it. It's very, very simple to do it, and it's great for an event by event processing. So this is the programming model of Pulsar functions. It's very reactive. Functions receive messages for one or more topics. As you can see here on the left, you can subscribe to as many ones as you want. Each time a message is received, The Pulsar function runtime takes your code that you've submitted and executes it against that particular message, and it can optionally output a message to another topic, like I mentioned before, so you can chain them together, do complex transformations, do step A, step B, step C. You can optionally also output to a log topic if you want to record metrics. That's something as well. You can increment counters, so you can measure the performance and monitor the performance of these Pulsar functions. But it's a very, very simplistic programming model, but it is event reactive. And that's the key. An event comes in, you process it. So it fits the EDA style perfectly. It even has an event handler style API as shown here. So it is a very, very simple, easy to understand API. So even a comp sci student year one can understand this. You have a method that comes in, your message comes in on the left, that's your input string, whatever the message is, and then you can process it, and if you return it, that's your publication of the output message as well. So very, very easy. If you can implement a single method in a programming language of your choice, like Java or Go or Python or now Node.js, you can write Pulsar functions very easily, and you don't need to learn any other API to do it. This is it. If you can execute this, you can already write Pulsar functions. Next, I want to talk about function mesh. So Pulsar functions are standalone units of code, and you can deploy them with Apache Pulsar tools. CLI tools exist to submit them one by one. But eventually, you build up enough of these functions. You get a couple hundred of those. You want to be able to deploy them in a more packaged and more efficient manner, for lack of a better term. Now, function mesh was invented to support the execution of multiple Pulsar functions, allows you to orchestrate them together into a single complex streaming job, so you can have 5 or 6 functions that do different processing to events as they come in, and you want all of those, they sort of depend on one another, and you want to submit them all together. If you make changes to them, you want to update them all together. Function mesh is built for that, and it utilizes under the covers the full power of the Kubernetes scheduler to manage and scale these Pulsar functions and connectors automatically, right? So it deploys them. It takes your code, you configure it with a CRD shown here. So you write some code, or you define it about how you want your application to run. So in this example here, we have 2 different functions. They have different image names, the number of replicas you have, configuration parameters, input, output, topics, etc., etc., so on and so forth. You have number 1, you have number 2, and you submit this, and the function mesh takes care of all the rest for you. It spins up the Kubernetes pods for you, gets them running, gets them subscribed to all the input topics, gets them publishing to the output topics, and it's very easy to, and then if you want to make a change, you make a change to this one file, you do an apply on that using the Kubernetes tooling, and it just automatically detects the changes and makes those changes for you automatically. So it's a very easy process to do, and it's all driven by a single definition file. So, talking about event-driven architectures and applications, we talked about how those are set up and run and how they're designed to do. But the purpose of this application, or this presentation rather, is to demonstrate resiliency and scalability of event-driven architectures. Right? It's not enough to have Pulsar to get resiliency. It's not enough to have Pulsar functions to do it. What you really need to do is have the Kubernetes operators and the function mesh and everything built up to handle all of these features for you automatically. So you can focus on your programming logic, and if you follow this pattern for deployment, then you will get the resiliency and scalability built in automatically. So covering the resiliency part is the Kubernetes runtime. Right? All function meshes are managed by the Pulsar function mesh operator, and under the covers it uses the Kubernetes replica sets to manage these instances. Now, replica sets, for those of you not familiar with it, just a Kubernetes concept that ensures that you have a set number of copies of a specific pod are always running. So you say, I want to have 5 instances of this particular function running. It's implemented as a replica set. Kubernetes detects if one of those pods stops working, the running count drops from 5 to 4 and automatically restarts that one for you. So that's your resiliency built in. If something causes your code to get an out of memory error or crash or something like that, you throw an exception, and it dies, Kubernetes automatically through the replica sets created by the function mesh provides that for you, and the resiliency is built in. Now, as we saw in the previous CRDs, you can specify a replica's parameter to specify the number of pods at a minimum you want. Generally, we recommend setting that to at least more than one for high availability. And depending on your subscription type, you can have more than that, obviously, and scale up, which we'll see in a minute. The other part of the equation is scalability, right? So it's not just enough to have instances restart over and over again. What happens if you have a large surge of data and you have an SLA around how long it takes me to process this data? I can't have a back pressure event where lots of events queue up and it takes me 5-10 minutes to process the latest ones. That might be too late. If I'm doing a real-time event processing engine, I want to, an event comes in, I need to react to it more quickly. So with Pulsar functions right now, there's a way to scale it. You can say Kubernetes scale, increase the number of replicas using that replica set, as I mentioned before, and override the default setting you set when you deployed it, right? So you deployed a function, you said, I want my replicas to be 1. Oh, now there's more data coming in. You have to be alerted to this. You can go into the command line and you can say scale my replicas from 1 to 2 or 2 to 3, and all of that happens automatically. But you don't, or that happens manually rather through manual intervention. What you really want to do is have auto scaling instead. You want your system to detect the fact that it's falling behind, that it's not keeping up, or that it's using too much memory or too much CPU, which is a sign that it's being overworked, and have it respond to that automatically. Right. So with that, you can leverage one of the built-in Kubernetes operators or autoscalers that come in, which are in HPA. You can scale horizontally, which means increase the number of replicas, or you can scale vertically, which means give me more memory, more CPU for a pod that I've already allocated because I'm running out of memory or running out of CPU, and I need more. Just note that it's an either-or proposition. You can't really do both. It'd be cool if you could do both, but right now you have to pick a strategy about how you're going to scale, and the function mesh will support that for you. So you can either do a vertical pod autoscaling, or you can do a horizontal pod autoscaling, but you can't have both. So how does this work within the function mesh for HPA? So horizontal scaling, right? So it monitors the number, all of your different pods, and you specify, I want my minimum replicas to be 3, my maximum is, let's say, 5, and then it monitors and measures the usage of your resources that you use to scale across all those pods and does an average. Right, so you're saying my threshold for CPU might be 80%, which we're going to do in the demo, but if all of your pods on average are only using 60%, it won't trigger an event, a scale event. But if once they get consistently over that threshold that you define, again as an average across all the pods, at that point it says, okay, it's time to trigger an auto-scaling event, and another pod will be added, another instance of your Pulsar function is added automatically. So by default, we have some built-in ones that are predefined and that you can say, I want to scale based on CPU or I want to scale on memory. And there's 6 of them total. Again, it's based on a percentage threshold of utilization of all of the replicas within your replica set on a per function basis. So what that means is you can say I'm setting my CPU average to be 50%. And if the average CPU across all these pods, as we saw here in this previous slide, if that average comes more than 50%, then I will increase the number of pods to get that average CPU down. You can also do it for memory, right? So if my memory utilization goes above 20%, 50%, 80%, that'll trigger the scaling event as well. So those are the built-in ones, and I will use one of those for the demo as well. Now, before you get started with this, you're ready to get started, you put it in the CRD, that's really not enough. You have to also make sure that first and foremost you have a metric server within your cluster, and that's a Kubernetes metric server, right? So this is for Kubernetes to use. It's for the Kubernetes scheduler to find this information, the metrics around the utilization on a pod level, and then you have to have the HPA, the autoscalers use that API to collect those metrics. So after to enable that, you must specify a max replicas parameter in there and set a value for it in that CRD, and it has to be greater than your default replicas, right? So your replica says I want to have 1 to start with. I can have max replicas of 3. Now you've basically told the function mesh that I want to use horizontal pod auto scaling for that. Secondly, you have to specify that you want to use which metric you want to use, whether it's memory-based or CPU-based metrics on that, and you put that under the pod.built-in autoscaler type, and we'll see that in one of the CRDs here in a second, and the default threshold. My default, or actually a threshold, and the default is average CPU of 80%, and we'll demonstrate that as well. But you can tweak that if you want. So showing that in code, here's an example of how you would specify this in reality with highlighting the two key features that you have to change. So let's say you have a simple Java-based Pulsar function. There's your class name, very generic. You set some basic properties. You set a replica of 1. I want to start with 1. But by adding that yellow line there that says max replicas of 4, you're now saying, I want to enable HPA. I want horizontal pod autoscaling to be available. And down in the pod section, you put in which built-in autoscaler you want to use there, and you can specify what your policy is, or what sort of trigger event you want it to do. In this case, I'm overriding the default of 80% and setting it to be average CPU of 20%. So it's going to trigger it very quickly on that. And then you put that in with all your other function configs, and when you deploy it using the function mesh, all of it will happen for you automatically. Now you can also override if the 80% and the 50% and the 20% aren't right for you for some reason. That isn't the right number. You can override it and set a custom value for yourself as well. So this is the same example, but instead you're going to set an average utilization of 45%, and this is how you do it. So again, you say auto scaling metrics. You choose the resource you want it to be. In this case, we're choosing CPU, but it can either be a CPU or memory. Those are your two options there. And then you can define the percentage, right? It's by utilization. Right now, utilization is the only type. And you can do average utilization of 45%. Now you're going to trigger this event, the scan event, not at 20%, but now 45%. If you want to do auto scaling with vertically instead, and you don't want to increase the number of replicas, then it's going to look at a similar scenario. I will show you how to configure that. So again, the scaling is based on the analysis of the historical resource utilization from the metric server, and then you sort of want to have it react to these sort of events as it comes in. So as your pods memory utilization becomes higher, CPU utilization becomes high, it will automatically increase the resource limits that you set on it to allow it to basically make a recommendation as well. That's the key difference here, that a VPA deployment has a recommendation around what the best next number as far as CPUs and memory is concerned. Whereas with HPA, you said I want to start with 1, I'll go up to this many. That's really it. There's no recommendation required, and it scales in the replicas as needed. With the vertical pod autoscaler, there's some additional analysis done as well, right? So the vertical pod autoscaling goes out and gets some recommendations for that. For example, updates the pods. Then we monitor the pods with a metric server there in the lower right-hand corner. It's monitoring the pods. It's getting some information, and then the VPA recommender can either say, "Hey, everything's fine. There's no thresholds being triggered. Everything's great," or it's saying, "Hey, this pod is using a lot of memory, so I'm going to make a recommendation that you increase your memory accordingly. Maybe double your memory size." Provides those recommendations back to the VPA. The VPA then passes them on to the updater. The updater manually updates your pods, or automatically updates the pods for you behind the scenes, increases the memory allocation to it, and then it does a measurement again. So it's a big cycle. Then it goes back and says, I made a recommendation, I've updated the memory, now let's look at the metrics for a little bit, let it bake in, see if it works. If everything's happy, we're fine. If not, we're going to adjust. Now your CPU goes up. Okay, let's adjust the CPU as well. And so it is a continuous feedback loop, and it's always trying to dial in your pods to the right number of cores and the right number or amount of RAM to be allocated to your Pulsar function. So we'll walk through the steps of how you enable it here as well. Again, you have to have the metric server available either way. That's obviously a requirement, as we mentioned before. The first step is to query the metric server, as we saw here in the lower right-hand corner. Without the metric server, none of this is going to work, right? Nothing will trigger recommendation. It won't work at all. So you have to have that enabled. Then you have to make sure that you enable it in the Kubernetes cluster itself. It has not been integrated directly with Kubernetes. by default. So each, depending on your Kubernetes provider, there's different steps to get your VPA, configured. I use micro K8s. Kind might use a different one. OpenShift might use a different one, and so follow that recommendation on how to do the different VPA, because everyone's slightly different implementation of that. But if you want to configure that and use it, this is how you do it. This is how you change your CRD relative to your Pulsar function to use the vertical pod autoscaler, right? So again, you ensure that you set your replicas to 2, but it's only a number of replicas. It can be 1, it can be 2, whatever. I picked 2 in this case to make sure that there's always live pods during the update process, because part of the VPA process of adjusting is to kill the pod and then start a new one. And so if you need to have a pod always available, you might want to have 2 around, so there's always at least something processing while the other one is doing an update. Then within the pod stanza itself, you put a VPA section underneath of that with a auto update policy of auto, and then you can specify what your container policies are as well. So you can say for all policies, if you want to have more granular control, but for right now we do a wildcard. So for all the containers, I want to have a minimum of this, this amount of CPU and memory, whatever you want to set, and this is my maximum. I'll let the VPA adjust accordingly, but it shall never exceed these theoretical maximums, and this is sort of a cap that you can set on that. So once you've set this in place, this is how you deploy a function with that, and it will work. Again, as long as you have your metric server enabled and your VPA, a vertical pod autoscaler, enabled for your Kubernetes flavor, then it's going to work just fine. If instead you want to change it to be just based on resource requests rather than resource limits, because there's limits and then there's requests, this is how you can specify the request policy. Again, within the VPA stanza, you set a resource policy, you do a wildcard for all the container names, and you say the controlled values are request only. So this basically, with this particular setting, you're delegating to the VPA recommender to control the resource requests rather than the limits. So it's going to automatically demand more stuff, which may cause out of memory errors and scheduling errors and things like that. So be aware of that rather than increasing your limits, you're increasing your requests. You're actually going to allocate requests more cores and CPU and RAM, and make sure that your Kubernetes environment has those resources available. Otherwise, your VPA, by requesting this and trying to request these limits and then not getting them, will fail and crash your pods. So this is something to be aware of when you're using this environment. And then you also can, last but not least, you have more granular control over if I want to control CPU. So the recommender can only say I want to make adjustments to CPU, but it can't tweak your memory settings, or vice versa, right? So the VPA makes recommendations for CPU and memory. You can choose to ignore those, basically, is what you're saying. The VPA can make whatever recommendations it wants here on CPU, and you'll honor those. Anything around memory, it's not going to be impacted. It's not going to adjust those limits or resource requests on your particular pods. And with that, we'll go ahead and switch to a live demonstration. So if you go to my repo for this demo, there's an autoscaling function demo repo. It's publicly available, and in there I have different configurations of different HPA and VPA deployments. I've written a couple of different Pulsar functions that basically are guaranteed to consume a lot of CPU or memory. So things like computing, finding all the prime numbers between 1 and a billion, calculating pi to 57 digits or whatever. These are all configured to do that automatically. I want to point out here that we're basically going to do one of these. We're going to do the HPA 80 CPU demonstration. So we're going to start with my fixed work simulator. We're going to have 2 instances to start. We're going to have 1 replica to start up to 8, and I've configured it to basically do waves of computing the primes. So I'll start one process computing all the primes, and then 30 seconds later, with this launch delay, I'll start a second instance of computing the primes. That'll guarantee to spike up the CPU. That'll trigger it above the 80% threshold, and then we'll be able to see the Kubernetes environment start up new pods based on that. Everything else is pretty self-explanatory. We're using a Pulsar cluster in my local environment, and has Kubernetes installed, as I mentioned before. So let's go ahead and look over at the demonstration. So switching over to the live demo now, we can go ahead and see that I've changed into the GitHub repo. The data is all here. So we'll go ahead and deploy the function mess using that file that we just looked at, the function deployment HPA CRD. Running this command, you can see that we get positive feedback. Now we'll go down into the bottom window here and see what was created. So we can see that we've started one instance, one replica of the function. It's up and running, and we can see monitoring here in the targets mode that there's no CPU right now. Nothing's running on this particular guy. We'll go ahead and make sure that he settles in, everything's running. Then to trigger it, we're going to have to go ahead and publish a message to that topic to kick off the work to get this thing running. So we'll go ahead and make sure it's settled in. Let's go ahead and get into the Pulsar broker itself here. So now we're inside the Pulsar broker. We'll go ahead and publish a single command to the topic that will kick off this function, which calculates all the values of pi, which is going to chew up a lot of CPU. How come we are not? Oops. Because we have to do this. Okay. Try it again. There we go. So we'll go ahead and publish the message using this command. Do a quick check of this, that it's still running. Nothing going on. It's just sitting around with nothing to do at 7% CPU, so it's not going to get auto-scaled. Now we've since published the message, and it should trigger the execution of that method. And now we can see the CPU starting to pick up 10%. Come on. Wait a few minutes for it to work. It's launched the first. Yep, now it's doing some work. It's gone above 80%. It's triggered at 84%. So we should very shortly see an auto-scaling event happen automatically. So the next thing we expect to see is a second function being spun up in response to this CPU getting very high. And that's exactly what we've seen now that we've seen a handful of these all get triggered all simultaneously. So it's scaled 4 more pods. And the CPU is continuing to rise because we're doing a very intensive computation here, and the auto-scaling is taking place. Maybe you can hear my computer winding up in the background as it's doing some more work. Right, so we can see the first one ran, and then for 30 seconds we've kicked off another instance of that computing of the prime. So now we have 5 or 6 of those running. The CPU continues to increase. And obviously we're going to continue to auto-scale up automatically. So we have 6 instances running, and we'll continue to scale. And now we've gotten up to our 8 total, and the CPU has gone down from the 400 we saw back to 98. So it's sort of adjusting back down and doing the processing. And so what we demonstrated here is through that configuration and throwing in a lot of work, that the horizontal pod auto-scaling works, right? It detected the CPU getting very high. Increased the number of functions. The number of functions took off some of the work, which dropped the CPU back down below, and all these functions are running. Well, thank you for coming to my talk. Hopefully you learned quite a bit and enjoyed the demonstration. Feel free to follow me on Twitter, connect with me on LinkedIn, and if you want to see the source code and try it out for yourself, my GitHub repo is here as well. So thank you so much, and have a great conference.